Far above the spinning blue planet we call Earth, beyond the shimmering curtain of atmosphere and the orbit of the moon, lies a vast ocean of darkness speckled with light, the deep, endless mystery of space. Tonight, as you settle in to relax, let your thoughts drift away from the world you know and join me as we explore the wonders of deep space, a place of infinite beauty, powerful forces, and profound questions. Imagine yourself floating silently, weightless, surrounded by the deep black velvet of the cosmos. There is no up or down, no north or south, only stars in every direction, twinkling with ancient light. These distant suns have burned for billions of years, each one a glowing sphere of nuclear fire, scattered across the fabric of the universe like pearls on an invisible thread. Let's begin our journey close to home, just outside Earth's atmosphere, in the realm of low Earth orbit. Here, hundreds of satellites circle our planet like metallic fireflies. Some provide the GPS signals we use to navigate, while others carry weather data, communications, or scientific instruments. The International Space Station glides silently through the darkness, a fragile outpost of humanity orbiting at 17,500 miles per hour. From here, we push further, past the orbit of the Moon, Earth's only natural satellite. The Moon has inspired poets, dreamers, and explorers for millennia. Its surface is pockmarked with craters from ancient impacts, and its gentle glow has accompanied countless nights of human history. But our voyage is only beginning. We sail past the Moon and into interplanetary space, the vast realm between planets. Though it seems empty, this space is filled with particles, dust, and the faint breath of the solar wind, a stream of charged particles blown from the sun. We move now toward the heart of our solar system. The sun is a massive ball of plasma, over 100 times wider than Earth. At its core, temperatures reach over 27 million degrees Fahrenheit, where hydrogen atoms are fused into helium, releasing energy that eventually makes its way to the surface and into space as sunlight. That light takes just over 8 minutes to reach Earth, crossing nearly 93 million miles of vacuum. Orbiting the Sun are the 8 planets of our solar system, each one unique. We pass Mercury first, a scorched, rocky world that swings tightly around the Sun. Then comes Venus, shrouded in thick clouds of sulfuric acid, with surface temperatures hot enough to melt lead. Earth comes next, a blue marble teeming with life. From space it appears fragile, encased in a thin shell of atmosphere. The oceans shimmer with sunlight, clouds drift across continents, and the lights of cities glow softly on the night side. Next is Mars, the red planet. Its dusty surface is carved with canyons, volcanoes, and the dry beds of ancient rivers. Robotic explorers trundle across its plains, seeking clues about its past and the possibility of life. Beyond Mars lies the asteroid belt, a vast ring of rocky debris left over from the formation of the solar system. Though popular imagination paints it as a crowded field of tumbling rocks, in reality, the asteroids are spread out, with millions of miles between them. As we drift through the belt, we encounter the giant planets, Jupiter and Saturn. Jupiter is a massive gas giant, more than 1,300 times the size of Earth. Its swirling clouds and massive storms, including the iconic Great Red Spot, are mesmerizing. Dozens of moons orbit it, including Europa, which may hide an ocean of liquid water beneath its icy shell. Saturn follows, wrapped in its majestic rings made of ice and rock. Its moons, too, are wondrous, like Titan, with its methane lakes and dense atmosphere, or Enceladus, which spews icy plumes into space from hidden subsurface seas. Farther out still are the ice giants, Uranus and Neptune. Uranus spins on its side, while Neptune, with its deep blue hue, hosts some of the fastest winds in the solar system. And beyond them all lies the Kuiper Belt, home to dwarf planets like Pluto, Eris, and Makemake. These icy remnants whisper the secrets of the early solar system, orbiting in the cold, dark frontier. But our journey doesn't stop there. We are now approaching the edge of the solar system, where the solar wind weakens and the interstellar medium begins. Here lies the heliopause, the boundary between our sun's influence and the true emptiness of interstellar space. In this vast, silent region, the Voyager spacecrafts drift. Tiny ambassadors of humanity, launched in the 1970s, still sending back whispers of data from more than 14 billion miles away. Each carries a golden record, a time capsule with sounds and images from Earth, in case they are ever found by intelligent life. And now we pass into the realm between the stars, interstellar space. Here the distances are vast beyond comprehension. The nearest star to our Sun is Proxima Centauri, over 4 light-years away. That means the light we see from it tonight left over 4 years ago. If we traveled at the speed of the fastest spacecraft ever built, it would still take us tens of thousands of years to reach it. Yet even in this darkness, the universe is alive with wonders. Nebulae, clouds of gas and dust, glow in vibrant hues, birthing new stars within their depths. Some stretch for dozens of light-years, sculpted by stellar winds and radiation into towers and filaments. The Orion Nebula, the Eagle Nebula's pillars of creation, and the Horsehead Nebula, each one a cosmic nursery where the cycle of life begins anew. We come now to the stars, blazing spheres of light and fire scattered throughout the galaxy. Some are small and cool, like red dwarfs, while others are massive and short-lived, destined to explode in spectacular supernovae. Binary stars dance in pairs, and clusters of stars form glittering jewels in the blackness. And beyond them, swirling in the darkness, are the galaxies, vast islands of stars, gas and dark matter. The Milky Way, our home galaxy, contains hundreds of billions of stars. From the edge, it would look like a luminous spiral, arms stretching out into the void, wrapped around a central bulge. Nearby, the Andromeda Galaxy approaches slowly, on a course to merge with the Milky Way, in a dance that will take billions of years. Further out, countless other galaxies, spiral, elliptical, irregular, fill the observable universe. Each one holds its own mysteries, its own wonders, its own possible civilizations. And there, in the space between galaxies, lies the great cosmic void, regions of emptiness where not even a single galaxy can be found for millions of light-years. These are the silent halls of the cosmos, the vast unknown. But the most mysterious objects of all are perhaps the black holes, collapsed stars so dense that not even light can escape their gravity. At the heart of nearly every galaxy, including ours, lies a supermassive black hole, millions or billions of times the mass of the Sun. These cosmic titans shape the galaxies around them, bending time and space itself. Even time flows differently near such extreme objects. Einstein's theory of relativity tells us that gravity warps the fabric of space-time. Near a black hole, time slows to a crawl. If you could somehow hover just above the event horizon, hours for you might pass as centuries for someone far away. And then there is dark matter, the invisible substance that makes up most of the mass in the universe. We cannot see it, but we know it's there by the way galaxies move and spin. And dark energy, the mysterious force driving the expansion of the universe ever faster. The universe is not only expanding, it's accelerating. The galaxies are racing away from each other, their light stretched into red by the growing space between them. And one day, perhaps billions or trillions of years from now, even the stars themselves will fade, leaving a universe cold and dark, a place of silence, starlight long gone, memory lingering. But that is far in the future. For now, we are here, adrift in a vast and beautiful universe, full of light and wonder. Let your mind float freely through the stars. Let the infinite expanse cradle your thoughts, and rest in the comfort that you are a part of this grand and mysterious cosmos, a universe full of secrets and full of awe. The Sun is a massive ball of plasma, over 100 times wider than Earth. At its core, temperatures reach over 27 million degrees Fahrenheit, where hydrogen atoms are fused into helium, releasing energy that eventually makes its way to the surface and into space as sunlight. That light takes just over 8 minutes to reach Earth, crossing nearly 93 million miles of vacuum. Orbiting the Sun are the 8 planets of our solar system, each one unique. We pass Mercury first, a scorched, rocky world that swings tightly around the Sun. Then comes Venus, shrouded in thick clouds of sulfuric acid, with surface temperatures hot enough to melt lead. Earth comes next, a blue marble teeming with life. From space it appears fragile, encased in a thin shell of atmosphere. The oceans shimmer with sunlight, clouds drift across continents, and the lights of cities glow softly on the night side. Next is Mars, the red planet. Its dusty surface is carved with canyons, volcanoes, and the dry beds of ancient rivers. Robotic explorers trundle across its plains, seeking clues about its past and the possibility of life. Beyond Mars lies the asteroid belt, a vast ring of rocky debris left over from the formation of the solar system. Though popular imagination paints it as a crowded field of tumbling rocks, in reality, the asteroids are spread out, with millions of miles between them. As we drift through the belt, we encounter the giant planets, Jupiter and Saturn. Jupiter is a massive gas giant, more than 1,300 times the size of Earth. Its swirling clouds and massive storms, including the iconic Great Red Spot, are mesmerizing. Dozens of moons orbit it, including Europa, which may hide an ocean of liquid water beneath its icy shell. Saturn follows, wrapped in its majestic rings made of ice and rock. Its moons, too, are wondrous. Like Titan, with its methane lakes and dense atmosphere, or Enceladus, which spews icy plumes into space from hidden subsurface seas. Farther out still are the ice giants, Uranus and Neptune. Uranus spins on its side, while Neptune, with its deep blue hue, hosts some of the fastest winds in the solar system. And beyond them all lies the Kuiper Belt, home to dwarf planets like Pluto, Eris, and Makemake. These icy remnants whisper the secrets of the early solar system, orbiting in the cold, dark frontier. But our journey doesn't stop there. We are now approaching the edge of the solar system, where the solar wind weakens and the interstellar medium begins. Here lies the heliopause, the boundary between our sun's influence and the true emptiness of interstellar space. In this vast, silent region, the Voyager spacecrafts drift. Tiny ambassadors of humanity, launched in the 1970s, still sending back whispers of data from more than 14 billion miles away. Each carries a golden record, a time capsule with sounds and images from Earth in case they are ever found by intelligent life. And now, we pass into the realm between the stars, interstellar space. Here, the distances are vast beyond comprehension. The nearest star to our Sun is Proxima Centauri, over 4 light-years away. That means the light we see from it tonight left over 4 years ago. If we traveled at the speed of the fastest spacecraft ever built, it would still take us tens of thousands of years to reach it. Yet even in this darkness, the universe is alive with wonders. Nebulae, clouds of gas and dust, glow in vibrant hues, birthing new stars within their depths. Some stretch for dozens of light years, sculpted by stellar winds and radiation into towers and filaments. The Orion Nebula, the Eagle Nebula's pillars of creation, and the Horsehead Nebula, each one a cosmic nursery where the cycle of life begins anew. We come now to the stars, blazing spheres of light and fire scattered throughout the galaxy. Some are small and cool, like red dwarfs, while others are massive and short-lived, destined to explode in spectacular supernovae. Binary stars dance in pairs, and clusters of stars form glittering jewels in the blackness. And beyond them, swirling in the darkness, are the galaxies, vast islands of stars, gas, and dark matter. The Milky Way, our home galaxy, contains hundreds of billions of stars. From the edge, it would look like a luminous spiral, arms stretching out into the void, wrapped around a central bulge. Nearby, the Andromeda Galaxy approaches slowly, on a course to merge with the Milky Way in a dance that will take billions of years. Further out, countless other galaxies, spiral, elliptical, irregular, fill the observable universe. Each one holds its own mysteries, its own wonders, its own possible civilizations. And there, in the space between galaxies, lies the great cosmic void, regions of emptiness where not even a single galaxy can be found for millions of light years. These are the silent halls of the cosmos, the vast unknown. We now drift farther, beyond the spiraling galaxies, into the true abyss of the cosmos. As we glide past stars and their solar systems, we begin to explore the invisible, the forces and phenomena that shape the universe yet cannot be seen by the naked eye. First, there is gravity. the invisible architect of the cosmos. Though we cannot see it, gravity sculpts the universe on every scale. It pulls gas and dust together to form stars. It binds planets in orbit. It organizes galaxies, and it draws galaxies toward each other into clusters and superclusters. Its effects ripple across time and space. And gravity's most dramatic expression is the black hole, a region where gravity becomes so intense that space folds inward, creating a well so deep not even light can climb out. These aren't just theoretical concepts. Black holes are real, and they're found all across the universe. Some are the collapsed cores of dead stars. Others, known as supermassive black holes, lie at the centers of galaxies, millions or billions of times more massive than the Sun. If you could drift near a black hole, time itself would slow. This isn't science fiction. It's a prediction of Einstein's theory of general relativity, proven time and again. The closer you fall toward the event horizon, the point of no return, the more distorted your view of the universe becomes. Behind you, the stars would appear to rush together. Ahead, nothing but darkness. Yet black holes may also be engines of creation. The violence around them, the intense heat, the swirling matter, the jets of radiation flung out from their poles, may help seed new stars and regulate the growth of galaxies. In death, they may give birth. But beyond even black holes lies something more elusive: dark matter. We cannot see it, touch it, or interact with it directly. But we know it's there, by the way galaxies spin, by how they bend light, by the strange distribution of mass in the cosmos. Dark matter makes up most of the universe's mass, and yet we still don't know what it is. Perhaps it is made of particles we have yet to discover. Perhaps it is a property of space itself. Whatever it is, it holds galaxies together, forms scaffolds of cosmic structure, and silently governs the way the universe behaves. And then there is dark energy, the mysterious force accelerating the universe's expansion. Unlike gravity, which pulls things together, dark energy drives them apart. It stretches the fabric of space itself, pushing galaxies away from each other faster and faster. This was one of the most startling discoveries in modern science, that the universe is not just expanding but accelerating, and it implies a strange future. If the expansion continues, then one day, distant galaxies will fade beyond visibility. The sky will grow empty, and our cosmic neighborhood will become all that we can see. The ultimate fate of the universe remains unknown. Will it expand forever, growing colder and darker? Will it slow down and collapse in a big crunch? Or will it reach a mysterious equilibrium in some new, unknown phase? Some theories suggest a big rip, where the accelerating expansion tears galaxies, stars, planets, even atoms apart. Others speak of cyclic universes, endless loops of creation and destruction. These questions sit at the edge of science and philosophy, places where human understanding still falters. And while the far future of the cosmos is shrouded in uncertainty, its past, the origin of everything, begins with a brilliant flash: the Big Bang. Nearly 14 billion years ago, all the matter and energy in the universe was compressed into a single, unimaginably hot and dense point. Then, in an instant, it expanded, space itself stretching. time itself beginning. From that singularity arose the entire cosmos. In the earliest moments, the universe was a seething plasma, a fog of particles and radiation. As it expanded and cooled, atoms began to form. Light broke free. Stars and galaxies condensed from the primordial soup. And from the explosions of early stars, heavier elements were born. The ingredients for planets, for life, for us. We are stardust. The calcium in your bones, the iron in your blood, the oxygen you breathe, all forged in the hearts of stars that lived and died billions of years ago. We are, quite literally, the universe becoming aware of itself. And as we gaze deeper into the night sky, we are looking back in time. The farther away an object is, the older the light we receive. With powerful telescopes, we can glimpse galaxies as they were when the universe was still in its infancy, baby galaxies swaddled in gas, flickering with the birth of new stars. And now, we return to one of the most beautiful sights in the cosmos, the galaxy itself. If you've ever looked up at the night sky and seen the Milky Way as a silvery river of stars stretching across the heavens, you've glimpsed the disk of our galaxy from the inside. We orbit the center of this spiral galaxy once every 230 million years, carried along by the gravity of hundreds of billions of stars. Our solar system lies in one of its minor arms, a quiet corner of a vast and dynamic structure. From this vantage point, we can feel a sense of scale that both humbles and uplifts. We are tiny, yes, but we are also a part of something vast, ancient, and full of wonder. In the great silence of space, time flows differently, not just in the way gravity bends it, but in the way it is measured across cosmic distances. Human time, minutes, hours, years, begins to lose meaning when compared to the grand timelines of stars and galaxies. Consider a star like our Sun. It is about 4.6 billion years old and has another 5 billion years to go before it runs out of fuel. That means its lifespan is measured not in centuries, but in eons. A human lifetime compared to this is a flicker, a heartbeat in cosmic time. As stars age, they change. Our sun will grow hotter and larger, eventually becoming a red giant. It will expand, possibly engulfing the inner planets, including Earth. Then, it will shed its outer layers into space, creating a glowing shell of gas called a planetary nebula. At its heart, the core will collapse into a white dwarf, a dense, smoldering ember the size of Earth, but with half the mass of the Sun. More massive stars live fast and die young. After a few million years, they burn through their fuel violently, ending their lives in titanic explosions called supernovae. These are among the most powerful events in the universe, shining brighter than entire galaxies for brief periods. What remains after such a detonation is either a neutron star, a city-sized object so dense a teaspoon would weigh billions of tons, or a black hole. But not all motion in the cosmos is violent or explosive. Much of it is rhythmic, elegant, and serene. Planets orbit stars. Moons orbit planets. Binary stars swirl around each other. Galaxies spin slowly, like cosmic whirlpools. There are cosmic dances happening everywhere, slow ballets of motion that unfold over millennia. Some systems are so finely balanced that even a slight gravitational nudge can shift the entire rhythm, sending planets careening or stars merging in flashes of energy. And beyond motion, there are cycles. Stars are born, live, and die, and from their ashes, new stars form. The elements forged in dying stars become the building blocks of planets, and from those planets, perhaps life. One of the most astonishing ideas in modern cosmology is the possibility of life elsewhere in the universe. For decades, we have wondered whether Earth is unique, but in recent years, we've discovered thousands of exoplanets, planets orbiting stars outside our solar system. Some of these are Earth-like in size and temperature. Some lie in the so-called habitable zone, where liquid water could exist, and some orbit stars very much like our own. The ingredients for life, water, carbon, energy, appear to be common. Life, perhaps, is not rare, but inevitable. If life exists out there, it might be microbial, or it might be intelligent. It might look nothing like us. It might be thriving on a world under an ice-covered ocean, heated by the warmth of a planet's core. Or it might live in floating cities above the clouds of a gas giant. It could even be non-biological, life made of circuits, algorithms, and light. And if intelligent life has arisen elsewhere, what might it know? How might it view the universe? Could it see us? Would it recognize our golden records, our radio transmissions, our infrared heat signatures? The search for life is not just about aliens, it's a mirror for ourselves, a way to ask, who are we? What do we hope to find? And how will we react if we discover we are not alone? In the meantime, our own journey continues. Let us drift now toward one of the oldest and most mysterious forces in the universe, light itself. Light is more than what we see. It is energy, wave, and particle, vibrating through the fabric of space. From radio waves to gamma rays, the electromagnetic spectrum is how we understand the cosmos. Telescopes, tuned to different wavelengths, reveal galaxies invisible to the naked eye. Galaxies of cold hydrogen, of X-ray jets, of microwave echoes from the birth of time. And then there is cosmic background radiation, the oldest light in the universe. It fills every corner of space, a faint afterglow of the Big Bang, imprinted on the cosmos like a fossil. When we look at it, we see the universe as it was nearly 14 billion years ago, hot, dense, and just beginning to take shape. This light is a kind of memory, a whisper from the beginning of time. It reminds us that everything we see today, the stars, the galaxies, the atoms of your body, were once part of that singular flash, long ago. Even now, photons from distant stars travel across the void, racing at the speed of light for thousands or millions of years, only to end their journey when they strike your eye or a telescope's mirror. In seeing them, you are catching ancient messages delivered across the abyss. This interplay of space, time, and light is what makes astronomy not just a science, but a form of time travel. Every time we look up, we see the past, and in doing so, we learn not only about distant places, but about our own origins, and perhaps our future. Imagine now that we zoom out, far beyond individual stars, beyond planetary systems, beyond even our galaxy. From this vantage point, we begin to see the universe's largest structures, patterns etched across hundreds of millions of light years. Galaxies are not scattered randomly across the sky. They form groups, clusters, and vast filaments in a structure known as the cosmic web. Picture it, an intricate lace of glowing threads where clusters of galaxies lie at the intersections like bright knots in a spider's web. Between the threads are voids, immense, empty regions where almost nothing resides. This is the true shape of the universe on the grandest scales, and it's a shape shaped not by visible matter alone, but by the invisible scaffolding of dark matter. It was dark matter that seeded the formation of galaxies, drawing gas and dust together, guiding the evolution of cosmic structure over billions of years. Each galaxy within this web is a universe unto itself. Some are quiet spirals, spinning gently, their arms dotted with star-forming regions. Others are elliptical and old, their stars long past their prime. Some galaxies collide and merge, triggering bursts of star birth and reshaping their forms. The Milky Way, our home, is part of a local group, a small gathering of a few dozen galaxies, and that group lies on the edge of a much larger structure, the Virgo supercluster. This, in turn, is part of an even larger flow of galaxies streaming toward a gravitational anomaly we call the Great Attractor, a region so massive it bends the motion of entire galactic families. Beyond even that lies Laniakea, a supercluster so vast it defies imagination. Over 500 million light-years across, home to over 100,000 galaxies. It's our address in the cosmic hierarchy: Earth, Solar System, Milky Way, Local Group, Virgo Supercluster, Laniakea. And yet, despite all this grandeur, the universe is surprisingly uniform on the largest scales. No matter which direction you look, the cosmos looks much the same, a principle known as cosmological isotropy. It suggests that there is no special place in the universe, no privileged center. We are not in a unique location. We are simply part of the whole. This realization has a quiet beauty to it. It reminds us that the universe does not revolve around us, and yet it includes us. We are woven into its fabric, connected to stars, to galaxies, to the very expansion of space. That expansion is still happening. The space between galaxies stretches. Light traveling across it is stretched too, redshifted, shifted toward longer, cooler wavelengths. This is one way we know the universe is growing, and growing faster than before. Astronomers measure this expansion using distant Type Ia supernovae, stellar explosions so luminous and predictable that they serve as cosmic mile markers. By comparing their brightness with their redshift, we can estimate how far they are and how fast they're receding. It was through these measurements that we discovered dark energy, the mysterious force accelerating the universe. And from this data, we estimate the age of the universe to be about 13.8 billion years. But what came before? That question takes us into the realm of theory, where cosmologists explore ideas like the multiverse, the possibility that our universe is just one of many. In this view, what we call everything may be just one bubble in a vast sea of cosmic foam, each bubble its own universe with its own laws of physics. Some might be wildly different, with different forms of matter, different strengths of gravity, or even no stars at all. Others might be eerily similar. And perhaps, somewhere out there, a version of you is listening to this same story under a different sky. It's impossible to say for sure, but these ideas remind us of something profound, that the universe is not static. It is not complete. It is a story still being written, a canvas still being painted, one photon at a time. And within that story, we play a small but conscious part. We are the only creatures, as far as we know, able to look back on the cosmos, to ponder it, to wonder. In doing so, we've created observatories, satellites, and massive instruments like the James Webb Space Telescope. This next generation eye will peer deeper into space than ever before, capturing the light of the first stars, the first galaxies, the birth of starlight itself. Each discovery adds a brushstroke to our picture of the universe. Each answer raises new questions, and so the journey continues. But for now, as we float among galaxies and clusters in the quiet embrace of space, let your mind drift gently. The stars are your companions, the void is your blanket, and the rhythm of the cosmos is your lullaby. As we drift through this magnificent tapestry of stars and voids, a deeper sense of awe begins to settle in. Not just scientific wonder, though that alone is vast, but something more human, more personal, the poetry of the cosmos. Throughout history, humans have gazed at the night sky and found meaning. The ancients charted constellations, stories written in the stars. Orion, the hunter, Cassiopeia, the queen, Draco, the dragon. To early civilizations, the sky was a calendar, a guide, a divine script. Eclipses were omens, comets were messengers. In cultures across the world, the stars became part of our myths, our rituals, and our longing. They reminded us of gods, of ancestors, of dreams. And even today, as we peer at them with telescopes instead of telescopic eyes, that sense of story remains. The universe is not just a place of numbers and particles. It is also a place of beauty, rhythm, and resonance. Pulsars, the collapsed remnants of stars, spin and pulse like cosmic metronomes, sending out precise radio beats across the void. Some rotate hundreds of times per second, perfect in their timing. There are stars that brighten and dim with eerie regularity, Cepheid variables, whose pulsations allow us to measure distance across the universe. Their flickering is like the heartbeat of space itself. Then there are gravitational waves, ripples in the fabric of space-time, predicted by Einstein and first detected in 2015. They arrive not as light, but as trembling in reality itself, caused by the collision of black holes or neutron stars. When we detect them, we are listening to the echoes of titanic cosmic events, not with eyes, but with feeling. Each of these phenomena is a reminder that the universe is not still. It hums, it moves, it sings. And somewhere in this great song, our tiny Earth orbits a quiet star in a spiral arm of a galaxy among hundreds of billions. And on this Earth, life has bloomed. Minds have awakened. Consciousness has arisen. It is easy to feel small when confronted with the scale of the cosmos. But perhaps it is better to feel connected. For all our size, we are made of stardust. We are nature's way of understanding itself, and that gives our existence a quiet nobility. We build observatories not just to measure, but to wonder. We ask not just how, but why. We write poetry about the stars. We compose music to echo their silence. We paint galaxies in the colors of our imagination, and in our quietest hours, in the still of night, under the hush of twilight, we look up and feel something ancient stir within us. A longing, a memory, a sense that we are part of something far greater than ourselves. The philosopher Carl Sagan once said, "We are a way for the cosmos to know itself," and perhaps he was right. Through us, the universe has eyes. Through us, it can dream. So tonight, as you rest beneath the stars, whether you can see them or not, let this thought stay with you. You are part of this universe. You are made of its dust, shaped by its gravity, lit by its stars. You are a child of time, a voyager of space, a seeker of meaning. And though the galaxies may be far, and the stars countless, you are never separate from them. You are woven into their story, as much a part of the cosmos as the light that shines across it. Let us gently return now, through the spiral arms of the Milky Way, past the stars and gas clouds, toward the modest yellow star that warms our home. We draw closer to Earth, small, delicate, radiant in the darkness. From a cosmic perspective, Earth is a pale blue dot, suspended in a sunbeam. That phrase, coined by Carl Sagan, comes from a photograph taken by the Voyager 1 spacecraft in 1990. As Voyager prepared to leave the solar system, scientists turned its camera backward for one last look. The image it captured showed Earth as a tiny speck, less than a pixel wide, floating in the vastness. Every person who has ever lived, every war, every act of kindness, every sorrow, every hope, all of it has unfolded on that single dot. To see Earth from afar is to recognize its fragility. Its thin atmosphere protects us, sustains life, shields us from radiation. The oceans cradle life. The land bears forests, deserts, mountains, and rivers. And in the invisible weave of societies and stories, humanity stirs. For all the harshness of the cosmos, its vacuum, its radiation, its silence, Earth is a sanctuary. The balance of its systems, the presence of water, the interplay of energy and chemistry have made it uniquely hospitable to life. And not just life, but intelligence, reflection, creativity, love. In the cosmic ocean, Earth is an island oasis, and we, its sentient inhabitants, are its caretakers and its questioners. We build machines that reach for the stars. We send signals into space. We write messages into golden records and launch them on trajectories that will outlast us. We name the stars. We map their motions. We seek their companionship. But as we explore outward, we are also learning to look inward, to care for this world, to protect its fragile systems, to preserve its wonders for those who come after. For the same telescopes that reveal galaxies also show us our own thin layer of atmosphere, its rising carbon dioxide, its shifting patterns. The same science that studies Mars tells us what happens when a planet loses its magnetic shield or when greenhouse gases spiral out of control. Earth is not guaranteed. Its stability is a gift, a moment in time. And as we marvel at the universe, we must also cherish the tiny patch of it we call home. To float above Earth in orbit is to see no borders, just continents and oceans, clouds drifting, storms forming, lights flickering in the dark. It is a view that humbles and unites. Astronauts call this the overview effect, a shift in perspective, a realization that we are one species on one planet, spinning in space together. And from this view, our divisions seem petty, our conflicts small. What matters is life, beauty, continuity, wonder. So tonight, as you lay down and listen, think of this planet not just as a home, but as a miracle, a cosmic coincidence wrapped in sunlight and gravity, a blue marble turning gently in a sea of stars. Let that thought comfort you. Let it hold you. Because while the universe is vast and ancient, there is nowhere quite like Earth. And in the quiet of night, when the stars shine down, we are all part of something vast and something beautiful. As we rest near Earth, watching it turn silently beneath the stars, our minds drift to the future, to the search, the waiting, the possibility that someone, somewhere, might be listening. For over a century, humanity has been sending radio waves into space, not intentionally at first, but as a byproduct of our technology. Our first broadcasts, like the 1936 Olympics or early radio transmissions, have already traveled over 80 light years away, touching thousands of stars and their planets. And yet, the silence remains. We've searched the skies with radio telescopes, listening for patterns, signals, anything that might suggest intelligence. Projects like SETI, the search for extraterrestrial intelligence, scan the sky night after night, ears tuned to the cosmos. So far, no reply, no signal, no confirmation. But maybe that's not surprising. The universe is vast, and time is long. Civilizations may rise and fall like waves. Maybe we've missed each other. Maybe they're too far away. Or maybe they are listening too, just like us, waiting for a voice in the dark. And maybe that voice is already out there, carried on the Voyager spacecrafts, on their golden records, etched with greetings, music, sounds of Earth, and images of life. These records are more than data. They are symbols, declarations of curiosity, of hope, of our desire not to be alone. In the silence of deep space, they drift onward. It will take tens of thousands of years for them to pass even the nearest stars. But they continue, bearing messages from a tiny planet orbiting a modest star. These records were created by people who will never see where they go. And perhaps that's the beauty of it. A gesture made not for gain, but for meaning. A message launched into the abyss because we believe in connection. And so we wait. We listen. We dream. In the meantime, we also build our understanding of the universe, not just in telescopes and equations, but in art, in stories, in music. We turn the stars into metaphors. We sing about moonlight, paint galaxies, write novels that explore other worlds. The universe has become a canvas for the human imagination. And why not? It's the greatest story there is. A tale of creation, evolution, expansion, and mystery. A story we are a part of. And so, with each new discovery, a new exoplanet, a new distant galaxy, a new ripple in space-time, we learn a little more. We adjust our place in the cosmos. We grow. That's what makes the wonders of deep space so moving. Not just that they are beautiful or vast, but that they challenge us to reach, not only across the stars, but into ourselves, to ask deeper questions, to seek deeper truths, to become more than what we were. This search is not separate from sleep, from dreaming. In fact, sleep may be the perfect place for it. As the body rests, the mind can float freely, through time, through possibility, through the great quiet of space. So tonight, as your breath slows and your thoughts soften, imagine yourself once more drifting through the stars. There is no urgency, no destination, only calm, only wonder. The stars do not rush, the galaxies do not hurry, and neither must you. Let yourself float, let your mind wander, and let the universe hold you gently as it has for billions of years. There is something deeply comforting about knowing the universe goes on, that while we sleep, stars are born, galaxies spin, and light continues its journey across the vast dark. Out there, in the cold and silence, time stretches gently. No ticking clocks, no deadlines, just the rhythm of expansion, the slow swirl of cosmic structure. If you could lie on the surface of a still planet, somewhere far from city lights and atmosphere, you would see the universe in its fullness. Millions of stars overhead, streaks of glowing nebulae, the soft curve of your galaxy's arm stretching from horizon to horizon. And perhaps, in that moment, you'd feel no fear, no urgency, just stillness, just the knowledge that this is your place, not just the planet beneath you, but the cosmos itself. We are not separate from the stars. We are born of them. Their atoms flow through us. Their light touches our skin. Their gravity tethers us. And when we sleep, truly sleep, not just in rest, but in peace, it is as though we return to the same silence from which we came. The darkness of space is not empty. It is full of potential, of mystery, of subtle movement. It is not cold in a hostile sense, but in a quiet, ancient one, like the hush of snowfall or the depths of a calm sea. Even death in the universe is not an end, but a transformation. A star that collapses into a neutron core or black hole is still part of the fabric, still influencing space around it. The particles it shed become part of nebulae, from which new stars and planets may form. This continuity, this recycling of matter and energy, is the essence of the universe's beauty. Nothing is wasted. Nothing is truly lost. It is all motion, all story. So, as you settle deeper into rest, know that you are part of that rhythm, that your thoughts, your dreams, your very breath, they are echoes of cosmic history. In the silence between each heartbeat, there is space. In the warmth of your blanket, there is starlight. In the stillness of sleep, there is time to drift far and wide, to float among the spirals of distant galaxies, to brush past comets and suns, to listen to the hum of the universe. You do not need to go anywhere. The universe is already within you. Its atoms are your atoms. Its story is your story. And as you slip into sleep, may that thought bring you peace. You are cradled in starlight, carried by gravity, sung to by radiation, older than worlds. You are not alone. You are never alone. Rest Traveler of time and space, the cosmos will keep its watch. Time in the universe is not the same as time in a room. It stretches, it warps, it moves quietly beneath everything, not in a straight line, but like a flowing river, sometimes fast, sometimes slow, and sometimes standing still in pools of cosmic silence. When we speak of time and space, we are often speaking in scales so large they slip through the fingers of the human mind. Billions of years, trillions to come. Galaxies that formed when the universe was young still shine in the dark, their ancient light just now arriving at our telescopes, telling us stories from an age when Earth had not yet formed. And yet, among these endless eons, there are smaller moments, more intimate ones. A star's gentle flicker, a moon's quiet passage across a sky, the brief, dazzling flash of a meteor as it burns up in an atmosphere. These are moments we can feel. They pass through us like breath. It's important to remember that the universe is not just grand, it is patient. Stars take millions of years to form, planets cool slowly, orbits shift in cycles of tens of thousands of years. Everything that feels fast in our world, storms, lifetimes, generations, is, from a cosmic point of view, a blink. And yet, within these brief lives, we ask immense questions. Where did we come from? Why are we here? What does it mean to exist? The answers are not always loud. Often, they are whispers, hints in the symmetry of a spiral galaxy, clues in the cosmic microwave background, insights from equations scrawled by candlelight or typed late at night by glowing screen. Echoes in the silence. Consider a photon, a particle of light. It may be created in the heart of a star, begin a journey that lasts millions of years, travel through the vacuum of space at the speed limit of the universe, and eventually reach Earth, entering your eye and striking a single cell on your retina. In that moment, it ends its journey. It becomes sight. It becomes meaning. Each time you look at a star, you're completing a story that began long before you were born. That's not poetry. That's physics. And it's beautiful. We exist in a web of moments like this, billions of them, constantly unfolding. All around us, the universe continues its vast, deliberate work. Supernovae explode in galaxies we've never seen. Black holes consume gas clouds. Dust coalesces into new planets. Somewhere, perhaps, life arises. A cell divides. A spark of awareness is born. And here you are, in this single moment of your life, breathing gently, wrapped in quiet, listening to the story of space. That in itself is miraculous. Time will carry you forward. The earth will spin, and the stars will shift overhead. The moon will wax and wane. Seasons will change. But for now, you are still. You are safe. You are part of this. All the motion and chaos of the universe continues, and yet it leaves room for peace. In fact, that peace is part of the structure too. It's there in the quiet between pulsar beats, in the shadow of a ringed planet, in the long glide of a comet through the solar wind. It's here now, in your room, in your mind. You don't have to do anything. There is no task, no goal, only this moment, only this awareness. You are the universe, experiencing itself, slowly, softly, sweetly, drifting with time, wrapped in light. There's a subtle geometry woven through the fabric of space, a harmony that spans the scales. It's in the elegant spiral of galaxies, echoing the patterns of hurricanes and shells. It's in the symmetry of atoms, the curve of planetary orbits, the shape of magnetic fields stretching like invisible hands across the void. This geometry is not rigid. It breathes, it changes, it adapts to gravity, to energy, to time. It is the scaffolding upon which the universe paints its masterpiece. And as we move through this invisible architecture, we realize something profound. The universe is not just vast, it is coherent. It holds together not with glue or string, but with balance, with form, with laws that apply equally to all. These laws of motion, of energy, of light, do not change depending on where you are. A hydrogen atom behaves the same in your hand as it does a billion light years away. Gravity curves space the same way near Earth as it does near a black hole. This sameness, this quiet reliability, is one of the most comforting truths we know. Even in the face of chaos, exploding stars, colliding galaxies, the death of matter, there is order. Even entropy, the universe's drift toward disorder, follows rules. And nestled within these rules is the miracle of emergence, how simple things combine to create complexity, how particles become atoms, atoms become molecules, molecules form life, and life becomes thought. You, listening now, are the product of such emergence. Your consciousness is not something imposed from above. It's the natural outcome of a universe learning to reflect. Your thoughts are patterns in matter, your dreams, gentle ripples in the geometry of a brain. And this is the same geometry that governs the stars. In that sense, you are not small. You are not a part. You are a resonance, an echo of the structure of everything. And so, as you drift further into rest, you might imagine floating not just among stars, but among ideas, shapes, equations glowing faintly in the dark like constellations, each one a doorway to understanding. The golden ratio, P, Euler's identity. These are not human inventions. They are truths that existed long before language, waiting to be discovered. And they are everywhere, encoded in spirals of galaxies, in patterns of petals, in the dance of electrons. They are the silent music of the cosmos, and we, through our curiosity, have learned to hear it. Perhaps then, the universe is not just a machine or a wilderness. Perhaps it is also a poem, written in the language of mathematics, sung in the voice of gravity, illustrated in the brushstrokes of light. And we are part of that poem, a verse unfolding in real time. The galaxies are not merely out there, they are also within. Every cell in your body contains atoms forged in ancient stars. Your heartbeat is measured in the rhythm of planetary time. Your breath is part of the cycle of worlds. Between the stars, the universe is not truly empty. It is filled with an extremely diffuse mixture of gas, dust, plasma, and magnetic fields, what scientists call the interstellar medium. This medium may seem insignificant due to its low density, but it plays a vital role in the life cycles of galaxies and the stars within them. Hydrogen makes up the majority of this material. In its neutral form, it's often invisible, detectable primarily through its faint 21 centimeter radio emission. When ionized by nearby stars or shock waves, hydrogen becomes luminous in emission nebulae, glowing with the light of recombination. These glowing regions often indicate zones of active star formation. Regions of denser gas and dust can collapse under gravity to form molecular clouds, cold, massive clouds where temperatures fall to just a few degrees above absolute zero. Inside these clouds, turbulence, magnetic pressure, and self-gravity create filaments and knots. Over time, some of these knots grow dense enough to form protostars. Galactic evolution is directly tied to the behavior of this medium. Spiral galaxies like the Milky Way are rich in gas and dust, with well-defined arms where density waves compress interstellar material, triggering star formation. Elliptical galaxies, by contrast, tend to be depleted of gas, their stellar populations dominated by older, redder stars. They form fewer new stars and gradually fade in brightness. Interactions between galaxies, collisions, tidal distortions, and mergers also play a significant role. When two galaxies merge, their interstellar media collide, compressing gas and initiating massive starbursts. In such events, thousands of stars may form within a few million years. These processes are critical for understanding galactic life cycles. As stars die, they return enriched material to the interstellar medium. Supernova explosions inject heavy elements like iron, nickel, and gold, along with energy and momentum. Planetary nebulae contribute carbon, nitrogen, and oxygen. This feedback both enriches and shapes the surrounding gas, influencing future generations of stars and planets. Moreover, active galactic nuclei, powered by supermassive black holes, can drive powerful outflows and jets that interact with the surrounding medium. These jets, composed of relativistic particles, can stretch for thousands of light years, regulating the availability of gas and potentially quenching star formation by heating or expelling it. On larger scales, entire galaxy clusters are embedded in a hot, X-ray emitting intracluster medium composed of ionized gas. This gas, while even more diffuse than the interstellar medium, contains a significant fraction of the baryonic matter in the universe. Its temperature and structure offer clues to both the history of galaxy formation and the distribution of dark matter within the cluster. The evolution of galaxies is not just a linear progression from gas to stars to stardust. It is a cycle, influenced by internal processes and external events. Star formation rates, the morphology of the galaxy, its mass, its environment, all contribute to its long-term development. The Milky Way itself is not static. It is currently absorbing smaller satellite galaxies. The Sagittarius Dwarf, for instance, is being stretched into streams of stars that arc across the galactic halo. In the future, in roughly 4 billion years, the Milky Way will merge with the Andromeda Galaxy. This collision will dramatically reshape both galaxies, likely resulting in a large elliptical galaxy over the following few billion years. During the merger, while individual stars are unlikely to collide due to the vast distances between them, the interstellar media of both galaxies will interact. Gas will compress, starbursts will ignite. The central black holes may eventually coalesce, releasing gravitational waves in the process. Such mergers are not rare. They are one of the primary drivers of galactic transformation across the universe. Observations of distant galaxies, seen as they were billions of years ago, often reveal distorted shapes, tails of stars, and luminous cores, all signs of past or ongoing collisions. These observations, made possible by deep field imaging from telescopes like Hubble and Webb, allow astronomers to reconstruct the universe's history. They show that galaxies were once more compact, more irregular, and more actively forming stars. Over time, structures grew through hierarchical assembly, smaller units combining to form the large galaxies and clusters we observe today. Understanding the interstellar medium and the processes of galactic interaction provides critical insight into how the universe came to look the way it does. It ties together the life of individual stars with the evolution of vast structures spanning millions of light years. Star formation begins in the coldest and darkest regions of space, molecular clouds. These clouds, often stretching across tens or hundreds of light years, are composed primarily of molecular hydrogen and trace elements like helium, carbon monoxide, and dust grains made of silicates and ices. Within these massive clouds, gravity competes with internal pressure, magnetic fields, and turbulence. Over time, localized regions, often triggered by external events such as the shock wave from a nearby supernova or the pressure from a spiral arm density wave, become unstable and begin to collapse under their own gravity. As a cloud core collapses, it begins to heat up. Conservation of angular momentum causes it to spin, flattening into a rotating disk of gas and dust. At the center, pressure and temperature rise until a protostar forms. Initially shrouded by its surrounding envelope, this embryonic star emits primarily in infrared, hidden from optical telescopes. As accretion continues, the protostar grows. Material spirals inward from the disk, while powerful jets of gas shoot outward along the poles, a signature phenomenon observed across many stages of star formation. These bipolar outflows help to regulate the infall of matter and clear the surrounding envelope. Eventually, when the core temperature exceeds approximately 10 million Kelvin, hydrogen fusion ignites. The protostar stabilizes and a new star is born. It enters the main sequence, the long stable phase during which it converts hydrogen into helium in its core, producing the energy that radiates as starlight. The lifetime of a star on the main sequence depends on its mass. Massive stars, more than 8 times the mass of the Sun, burn their fuel rapidly, lasting only a few million years. They shine brightly, often as blue or white giants. In contrast, low-mass stars like red dwarfs can persist for trillions of years, burning their hydrogen slowly and steadily. Around many forming stars, the surrounding disk of dust and gas becomes the birthplace of planets. Tiny grains collide, stick together, and grow. Over thousands to millions of years, these aggregates form planetesimals, the building blocks of planets. Through a process called runaway accretion, these objects can rapidly grow in mass, attracting more material and clearing their orbits. The result is a diverse planetary system. Closer to the star, rocky planets tend to form where volatile compounds have evaporated. Farther out, Beyond the so-called frost line, gas giants and icy bodies dominate. These systems may include moons, asteroid belts, comets, and dwarf planets, each contributing to the system's complexity. Eventually, the star exhausts the hydrogen in its core. What happens next depends on its mass. For Sun-like stars, the core contracts while the outer layers expand, creating a red giant. Fusion shifts to shells surrounding the core, fusing helium into carbon and oxygen. The outer layers become unstable and are gently expelled into space, forming a planetary nebula, a glowing shell of ionized gas. The remaining core becomes a white dwarf, slowly cooling over billions of years until it becomes a black dwarf. Though the universe is not yet old enough for any black dwarfs to exist. For massive stars, the end is more dramatic. After exhausting their nuclear fuel, they collapse suddenly, triggering a supernova, one of the most energetic events in the universe. The explosion disperses heavy elements into space, enriching the interstellar medium. The remnant core becomes either a neutron star, a dense object composed almost entirely of neutrons, or, if massive enough, a black hole. Neutron stars often rotate rapidly and emit beams of radiation, becoming observable as pulsars. Some are found in binary systems, where they siphon material from a companion star, producing intense X-ray emissions. These stellar remnants, white dwarfs, neutron stars, and black holes, can persist long after their progenitor stars have died, influencing nearby systems, merging with other remnants, or remaining as gravitational anchors for stellar clusters. Meanwhile, the elements they produce, carbon, oxygen, nitrogen, iron, and more, are swept into new clouds, where the cycle begins again. Each generation of stars is richer in heavy elements than the last. The Sun, for example, is a third-generation star, its composition bearing the signature of earlier supernovae. This recycling of matter creates the potential for complex chemistry and for life. Planets forming around metal-rich stars are more likely to have the ingredients for atmospheres, oceans, and biology. The connection between stars and life is not metaphorical, it is literal and chemical. In this way, stellar evolution is not only a process of energy conversion and matter transformation, it is the engine of complexity in the universe. Every atom in every cell of your body was once inside a star. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it forged in stellar hearts. Modern astronomy continues to refine our understanding of these processes. Instruments like the Atacama Large Millimeter, Submillimeter Array, ALMA, observe protoplanetary disks with stunning resolution, revealing the structure of young planetary systems. Space-based observatories like the James Webb Space Telescope peer through dust to witness the earliest stages of star formation in galaxies billions of light years away. Simulations running on supercomputers model entire galaxies, tracing the evolution of stars and gas through cosmic time. These models, compared with observation, help to constrain theories and reveal the complex interplay of physics on every scale. The story of star formation and stellar evolution is one of balance, between pressure and gravity, between isolation and interaction, between destruction and creation. It is a dance, billions of years in the making, choreographed by the laws of physics and executed in silence. As telescopes grew more powerful and methods more precise, astronomers began to uncover a truth long suspected, but never confirmed until the 1990s. Planets orbiting stars beyond our sun are not only real, but abundant. These are exoplanets, and their discovery has fundamentally reshaped our view of the universe. The first confirmed detection of an exoplanet came in 1992, orbiting a pulsar, a rapidly rotating neutron star. This was unexpected, yet it was only a few years later, in 1995, that the first exoplanet orbiting a sun-like star was found. 51 Pegasi b, a hot Jupiter orbiting very close to its star. Since then, missions such as Kepler, TESS, Transiting Exoplanet Survey Satellite, and ground-based observatories have identified thousands of exoplanets. As of now, more than 5,000 have been confirmed, with many more awaiting verification. Detection methods vary. The transit method, used by Kepler and TESS, watches for dips in a star's brightness caused by a planet passing in front of it. These tiny reductions in light, often less than 1%, allow astronomers to determine the planet's size and orbital period. The radial velocity method detects the gravitational tug a planet exerts on its host star, causing it to wobble slightly. This method is particularly effective at finding massive planets close to their stars. Other techniques include direct imaging, where astronomers block the star's light to photograph faint planets nearby, and gravitational microlensing, which uses the bending of light around a star and its planet to detect their presence. What we've discovered is staggering. Planets come in all sizes and configurations. There are gas giants with orbits tighter than Mercury's. There are rocky planets larger than Earth, known as super-Earths. Some orbit binary stars. Others drift alone, ejected from their systems, wandering through the galaxy in darkness. Some systems are tightly packed, with multiple planets orbiting within a zone smaller than Mercury's orbit. Others are vast, with massive planets far from their stars, likely formed through processes similar to binary star formation. Among this diversity, the most compelling targets are Earth-like planets in the habitable zone, the region around a star where temperatures might allow liquid water to exist. These planets, if they have the right atmospheres and conditions, could potentially support life. Planets like Kepler 452b, Proxima Centauri b, TRAPPIST-1e, and LHS 1140b are some of the most studied. The TRAPPIST-1 system, in particular, contains 7 Earth-sized planets, 3 of which are within the habitable zone. Located just 40 light-years away, this system offers one of the most promising opportunities for future study. To determine whether these planets are truly habitable, scientists analyze their atmospheres. The James Webb Space Telescope and upcoming missions aim to detect gases like oxygen, methane, water vapor, and carbon dioxide, potential biosignatures that, in the right ratios, could suggest biological activity. The study of exoplanets has also sparked interest in planetary habitability more broadly. Factors like a planet's magnetic field, rotation rate, atmospheric composition, and tectonic activity can influence its ability to support life. Some worlds may have subsurface oceans, like Europa, or Enceladus in our own solar system, warmed by tidal forces rather than sunlight. These environments, shielded from radiation, could offer stable niches for microbial life. The idea of life beyond Earth is no longer purely speculative. While we have not yet found it, the sheer number of planets, likely more than stars in the galaxy, makes it increasingly plausible. There may be tens of billions of habitable planets in the Milky Way alone. Astrobiology, the interdisciplinary science of life in the universe, seeks to answer fundamental questions. What are the conditions necessary for life? How does it arise? Could it evolve differently elsewhere? And if we do find life, what would it mean, scientifically, philosophically, culturally? Some scientists focus on extremophiles, life forms that thrive in extreme environments on Earth, to understand how robust life can be. Others study the origin of life, or develop models for hypothetical alien biochemistries. Still others consider how we might detect intelligent civilizations. This is the goal of SETI, which listens for signals that could indicate technology. So far, no confirmed messages have been received, but the search continues. Meanwhile, theoretical work explores what civilizations might do. Build Dyson spheres to capture starlight, send self-replicating probes across the galaxy, modify planets, or even stars. The Fermi paradox looms large in this discussion. If intelligent life is common, why haven't we found it? Solutions range from the rare Earth hypothesis to the possibility of self-destruction, to the idea that we're simply too early, or not looking in the right way. Regardless of the answer, the study of exoplanets continues to open windows into other worlds, some similar to ours, others entirely alien. Each one is a natural laboratory, a potential cradle of life, a chapter in the cosmic story. And we've only just begun. Future telescopes like the Nancy Grace Roman Space Telescope, LUVOIR, and HABEX will provide more detailed data, possibly even imaging Earth-like planets and detecting biosignatures. For the first time in history, humanity has the tools not only to imagine other worlds, but to observe them, measure them, and one day, perhaps, visit them. To understand the universe in its entirety, we must begin with its origin, the Big Bang. Contrary to the name, the Big Bang was not an explosion in space. It was the sudden expansion of space itself from an extremely hot, dense state, approximately 13.8 billion years ago. In the first fraction of a second, all of space and time, along with the fundamental forces and particles, emerged. The universe expanded rapidly during a phase known as cosmic inflation, smoothing out irregularities and setting the stage for the large-scale structure we observe today. As it expanded, the universe cooled. Within the first few minutes, nucleosynthesis occurred. Protons and neutrons combined to form the nuclei of hydrogen, helium, and small amounts of lithium and beryllium. These elements formed the primordial chemical foundation of the cosmos. For the next 380,000 years, the universe remained an opaque plasma. Photons scattered constantly off free electrons, preventing light from traveling far. But as the universe cooled further, electrons combined with nuclei to form neutral atoms, a process known as recombination. This allowed light to decouple from matter, resulting in the cosmic microwave background, CMB, radiation. The CMB, first detected in 1965, provides a snapshot of the universe at that early stage. Its faint, nearly uniform glow fills the sky, with tiny fluctuations that reflect the initial density differences, the seeds of all future structure. These variations, measured in exquisite detail by missions like COBE, WMAP, and Planck, inform models of cosmic evolution. Over the next hundreds of millions of years, the universe entered the cosmic dark ages, a time without stars, filled only with neutral hydrogen gas. Eventually, gravity caused regions of slightly higher density to collapse, forming the first stars and galaxies. This era, known as cosmic reionization, marked the universe's transition from darkness to light. The ultraviolet radiation from the first massive stars reionized the hydrogen gas, making the universe transparent once again. Galaxies began to form and evolve, assembling into larger structures through gravitational attraction. The large-scale structure of the universe is shaped by dark matter, an invisible substance that interacts gravitationally, but not electromagnetically. While it doesn't emit or absorb light, its presence can be inferred from galaxy rotation curves, gravitational lensing, and the distribution of galaxies. Dark matter forms a cosmic scaffolding, around which visible matter clumps. This structure resembles a vast web with filaments, nodes, and voids spanning hundreds of millions of light-years. Galaxy clusters lie at the intersections of filaments, while immense regions of empty space, or voids, stretch between them. Supercomputers simulate this structure by modeling billions of particles over cosmic time. These simulations, such as the Millennium Simulation and Illustris, reveal how small perturbations in the early universe grow into the rich tapestry of galaxies and clusters we observe today. Yet, the matter we can see, stars, gas, dust, comprises only about 5% of the universe's total content. Roughly 27% is dark matter, while the remaining 68% is dark energy, a mysterious force driving the accelerated expansion of the universe. The discovery of dark energy came in the late 1990s through observations of distant Type Ia supernovae. These stellar explosions, used as standard candles, revealed that galaxies were not merely receding, but doing so at an increasing rate. The nature of dark energy remains one of the biggest open questions in cosmology. It might be a property of space itself, the cosmological constant, or it could be a dynamic field known as quintessence. It could even indicate a deeper modification of gravity on cosmic scales. To describe the universe's evolution, cosmologists use the LCDM model, lambda cold dark matter. In this framework, lambda represents dark energy, while cold dark matter provides the gravitational glue that structures the universe. The model accurately fits observations from the CMB, galaxy surveys, and large-scale structures. This model also allows us to predict the future of the universe. If dark energy continues to dominate, the expansion will accelerate indefinitely. Galaxies will recede beyond our observational horizon. Star formation will slow as gas is exhausted. Over trillions of years, the universe will grow darker, colder, and more diffuse, a scenario known as the heat death or Big Freeze. Alternative scenarios exist depending on the behavior of dark energy. In a Big Rip, dark energy strength increases over time, eventually tearing apart galaxies, stars, and even atomic structures. In a big crunch, the universe might one day reverse its expansion, collapsing back into a dense singularity. Some theories propose cyclic models where the universe undergoes infinite cycles of expansion and contraction. Others explore multiverse concepts, where our universe is just one bubble in an infinite foam of possible realities, each with its own physical laws. While many of these ideas remain speculative, they represent the cutting edge of theoretical physics and cosmology, a frontier driven by both observation and imagination. Telescopes like the James Webb Space Telescope, Euclid, and future missions like LUVOIR and CMB-S4 aim to probe the early universe with greater precision, map dark matter more thoroughly, and understand the true nature of dark energy. The formation and structure of the universe is a story of immense timescales, invisible forces, and subtle symmetries. It spans from quantum fluctuations to cosmic filaments, from the first moments of time to the fate of all matter. Among the most mysterious and extreme phenomena in the universe are black holes, regions of space where gravity is so intense that nothing, not even light, can escape. They are not objects in the traditional sense, but distortions in the fabric of space-time itself. The concept of a black hole has its roots in general relativity, Einstein's theory of gravity. According to general relativity, massive objects cause space-time to curve. When a mass becomes sufficiently compact, this curvature becomes so steep that it forms an event horizon, a boundary beyond which nothing can return. Black holes can form through several mechanisms. The most common is the gravitational collapse of a massive star. When such a star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. If the remaining mass exceeds the Tolman-Oppenheimer-Volkoff limit, roughly 2 to 3 solar masses, the core collapses into a singularity, forming a stellar mass black hole. Stellar mass black holes are scattered throughout the galaxy. Some are detected through their effects on nearby stars, or by the intense X-ray emissions from matter accreting onto them. This matter, pulled from a companion star or surrounding gas cloud, forms an accretion disk, a swirling structure of heated plasma emitting enormous energy as it spirals inward. At the center of most large galaxies, including the Milky Way, lie supermassive black holes. These giants, with masses ranging from millions to billions of times that of the Sun, likely formed from the merger of smaller black holes and the collapse of massive primordial clouds in the early universe. The Milky Way's central black hole, Sagittarius A, is about 4 million solar masses and resides 26,000 light-years from Earth. Its presence was confirmed by tracking the orbits of nearby stars, which move at incredible speeds due to the black hole's gravitational pull. In 2019, the Event Horizon Telescope, EHT, produced the first direct image of a black hole's shadow, the silhouette of the supermassive black hole at the center of the galaxy M87. This historic achievement confirmed theoretical predictions about event horizons and further validated Einstein's equations under extreme conditions. Despite their name, black holes are not completely black. In the 1970s, Stephen Hawking demonstrated that black holes emit radiation due to quantum effects near the event horizon, a phenomenon now called Hawking radiation. This process allows black holes to lose mass over time and, theoretically, evaporate entirely given enough time. Hawking radiation bridges the gap between general relativity and quantum mechanics, hinting at a deeper theory of quantum gravity. However, it also leads to unresolved paradoxes, most notably the information paradox, which questions whether information about matter falling into a black hole is lost forever, violating quantum theory's core principle of reversibility. In addition to stellar and supermassive black holes, theorists also propose the existence of intermediate mass black holes, ranging from hundreds to thousands of solar masses. These may form through runaway collisions in dense star clusters or early universe conditions, though direct evidence remains elusive. There are also hypothetical primordial black holes, potentially formed from density fluctuations in the very early universe. These could range in mass from subatomic to thousands of solar masses. If they exist, they might contribute to dark matter or offer insight into the conditions of the first seconds after the Big Bang. Another frontier of black hole physics involves gravitational waves, ripples in space-time caused by the acceleration of massive objects. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first detection of such waves, produced by the merger of two stellar mass black holes over 1 billion light-years away. This discovery opened a new window into the universe. Gravitational wave astronomy allows scientists to detect otherwise invisible events, black hole mergers, neutron-star collisions, and to test general relativity in previously unreachable regimes. Ongoing observations by LIGO, Virgo, and CAGRA, and future missions like LISA, Laser Interferometer Space Antenna, will map the population of compact objects across the cosmos, revealing how black holes form, evolve, and influence their environments. Despite their fearsome reputation, black holes play crucial roles in galactic evolution. Supermassive black holes can regulate star formation by ejecting jets of high-energy particles, heating surrounding gas and limiting its ability to cool and condense. They are engines of some of the brightest objects in the universe, quasars and active galactic nuclei. As matter accretes onto these central black holes, it can emit more energy than an entire galaxy, visible across billions of light years. Black holes stretch our understanding of space, time, and matter. They challenge our theories, reveal the limits of current physics, and point the way to future discoveries. They remind us that the universe is not only vast, but profoundly complex, governed by principles we are only beginning to understand. In the aftermath of a supernova explosion, when a massive star dies in one of the most powerful events in the universe, what remains depends on the mass of the stellar core. If it is below the threshold for forming a black hole, the core collapses into an incredibly dense object known as a neutron star. Neutron stars are among the most exotic objects in the cosmos. Despite being only about 20 kilometers in diameter, roughly the size of a city, they contain more mass than the Sun. This makes their densities extraordinary. A single teaspoon of neutron star material would weigh billions of tons on Earth. The collapse that creates a neutron star forces protons and electrons to merge into neutrons, resulting in an object composed almost entirely of degenerate neutron matter. This matter is held up by neutron degeneracy pressure, a quantum mechanical effect that resists further compression. The structure of a neutron star is layered. The outer crust consists of a lattice of nuclei and a sea of electrons. Deeper inside, nuclei become more neutron-rich. Eventually, in the inner crust and core, matter transitions into a soup of free neutrons, exotic particles like hyperons, and possibly even quark matter, a state in which quarks, the fundamental constituents of neutrons and protons, exist freely. Above a certain mass limit, around 2.1 solar masses, though the exact value is uncertain, not even neutron degeneracy pressure can resist gravity, and the star collapses into a black hole. The maximum mass of a stable neutron star is still an open question and is a subject of intense research. Neutron stars are detected through their emissions, particularly when they manifest as pulsars. Pulsars are rapidly rotating neutron stars with intense magnetic fields. As they spin, they emit beams of electromagnetic radiation from their magnetic poles. If these beams sweep across Earth, we observe regular pulses of radio, X-ray, or gamma-ray signals. Some pulsars spin extremely rapidly, hundreds of times per second. These are millisecond pulsars, often spun up through accretion of material from a companion star in a binary system. They serve as incredibly precise cosmic clocks, useful for testing fundamental physics, measuring interstellar conditions, and even detecting gravitational waves through pulsar timing arrays. A particularly fascinating class of neutron stars are the magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. These fields are so powerful they can distort atomic structures and trigger starquakes on the crust, releasing energy as intense gamma-ray bursts. Neutron stars can exist in binary systems with other stars, neutron stars, or black holes. When two neutron stars spiral toward each other and merge, the collision produces gravitational waves and often an intense burst of electromagnetic radiation across the spectrum. Such an event was observed in 2017, GW 170817, the first detection of a kilonova, the optical counterpart to a neutron star merger. This groundbreaking observation confirmed that these mergers are a primary source of heavy elements like gold, platinum, and uranium, forged in the extreme neutron-rich environments and ejected into space. The combined gravitational and electromagnetic signals from GW 170817 provided a wealth of information, confirmation of neutron star mergers as sites of R-process nucleosynthesis, a new way to measure the Hubble constant, and insight into the equation of state of ultra-dense matter. The equation of state, the relationship between pressure and density inside neutron stars, remains one of the key unknowns in nuclear physics and astrophysics. Determining it would reveal the true nature of matter at the highest densities and could validate or rule out models of exotic states such as strange quark matter or Bose-Einstein condensates. New missions and observatories, like NICER on the International Space Station, aim to map neutron star radii and masses with greater accuracy. Future gravitational wave detections will further constrain models, especially from systems involving unequal mass binaries or tidal deformations during merger. The study of neutron stars sits at the intersection of astrophysics, particle physics, and general relativity. These objects offer laboratories far beyond what can be replicated on Earth. natural experiments in gravity, magnetism, and matter under extreme conditions. Understanding neutron stars not only explains one endpoint of stellar evolution, but also contributes to our broader knowledge of the universe's chemical enrichment, the dynamics of compact binaries, and the fabric of space-time itself. They are silent, ancient remnants of once luminous stars, spinning, pulsing, merging, shaping the cosmos long after their fiery origins have faded. Not all phenomena in the universe are gentle or quiet. Some are driven by incredible energies and reach us across vast distances in the form of particles and photons of astonishing intensity. These are the realms of high-energy astrophysics, a domain dominated by cosmic rays, gamma-ray bursts, and relativistic jets. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that travel through space at nearly the speed of light. Discovered in the early 20th century, these particles originate from a variety of astrophysical sources, including supernovae, active galactic nuclei, and possibly gamma-ray bursts. When cosmic rays collide with atoms in Earth's upper atmosphere, they create showers of secondary particles, including muons, pions, and neutrinos, which can be detected by ground-based instruments. These interactions are not only crucial for understanding particle physics, but also have implications for biology, climate, and even technology, as they can affect satellite systems and human activity in space. The highest energy cosmic rays, known as ultra-high energy cosmic rays, UHECRs, possess energies millions of times greater than what can be achieved by human-made particle accelerators like the Large Hadron Collider. Their exact sources remain a mystery, though they are thought to arise from the most extreme environments in the universe. Among the most powerful electromagnetic events observed are gamma-ray bursts, GRBs. These bursts release more energy in seconds than the Sun will emit over its entire 10 billion year lifetime. GRBs are typically classified into two types: short-duration bursts lasting less than 2 seconds, likely caused by neutron star mergers, and long-duration bursts associated with the collapse of massive stars into black holes, a process known as a collapsar. GRBs are detected by space-based observatories, such as NASA's Fermi Gamma Ray Space Telescope and the Swift Observatory. Their brief but intense light is often followed by an afterglow across the electromagnetic spectrum: X-rays, visible light, radio waves, allowing astronomers to pinpoint their host galaxies and measure their distances. Because GRBs are so luminous, they can be observed from billions of light years away, providing insight into star formation, galactic evolution, and the early universe. Some of the most distant GRBs detected occurred when the universe was less than 1 billion years old, making them valuable probes of cosmic history. Closely related to these phenomena are relativistic jets, narrow beams of charged particles moving at near-light speeds, ejected from the vicinity of compact objects like black holes or neutron stars. These jets arise when material accretes onto the object, often forming a rotating disk threaded by magnetic fields. The fields can funnel material into twin jets that escape along the poles. Jets from supermassive black holes in active galactic nuclei can extend for thousands of light years, glowing brightly in radio and X-ray wavelengths. These structures not only signal intense activity, but also influence the intergalactic medium, heating gas, and regulating star formation in galaxy clusters. In blazars, a subclass of active galaxies, one of the jets is oriented nearly toward Earth, resulting in extreme variability and brightness. These objects are key targets for multi-messenger astronomy, combining electromagnetic observations with neutrinos and gravitational waves. The study of high-energy astrophysics also encompasses X-ray binaries, accreting pulsars, magnetars, and supernova remnants, all systems where intense gravity and magnetic fields accelerate particles and emit radiation far beyond the visible spectrum. To observe these phenomena, astronomers rely on specialized observatories above Earth's atmosphere, which would otherwise absorb or scatter high-energy photons. Instruments like Chandra X-ray, Observatory, XMM Newton, NuSTAR, and Integral reveal the dynamic and violent processes shaping compact objects and energetic outflows. In recent years, multi-messenger astronomy has become increasingly important. This approach combines traditional light-based observations with data from gravitational waves, neutrinos, and cosmic rays. The detection of a high-energy neutrino from a blazar in 2017, correlated with gamma-ray emission, marked a new era in understanding particle acceleration in the cosmos. Efforts continue to trace cosmic ray origins with detectors like Pierre Auger Observatory in Argentina and IceCube Neutrino Observatory in Antarctica, which uses a cubic kilometer of Antarctic ice to detect faint flashes from neutrino interactions. These high-energy signals are not merely flashes in the dark. They are keys to unlocking the behavior of matter under the most extreme conditions, offering insight into black holes, stellar explosions, galactic dynamics, and even fundamental physics beyond the Standard Model. Though fleeting, they are among the brightest and most informative events in the universe, powerful bursts that carry the imprints of the most dramatic processes in nature. To understand the universe, we must understand the fabric it is made of, not just matter and energy, but space-time itself. Introduced in Einstein's theory of general relativity, space-time combines the three dimensions of space with one of time into a single, four-dimensional continuum. In classical Newtonian mechanics, time was absolute. It ticked forward uniformly for all observers, regardless of motion or position. But Einstein showed that time is relative. It stretches and compresses depending on gravity and velocity. This insight changed our understanding of the cosmos. A key concept in general relativity is that mass and energy curve space-time. This curvature tells matter how to move, and matter, in turn, tells space-time how to curve. It is not force that binds planets to stars or light to orbits around black holes. It is the shape of space-time itself. This curvature becomes more pronounced in regions of strong gravity. Near Earth, time slows slightly compared to higher altitudes, a phenomenon called gravitational time dilation. GPS satellites must account for this difference to provide accurate location data. Near a black hole, the effect becomes far more intense. To a distant observer, time near the event horizon appears to nearly freeze. Time is also affected by velocity. According to special relativity, moving clocks tick more slowly. This has been confirmed by observing particles like muons and by flying atomic clocks on jets. These effects become significant at speeds approaching that of light. In the broader universe, time is not uniform. It flows differently in different places and at different rates. The cosmic time used in cosmology refers to the age of the universe as measured by a hypothetical observer at rest with respect to the cosmic microwave background, a kind of universal average frame. The expansion of space further complicates our understanding of time. As the universe expands, light from distant galaxies is stretched, an effect known as redshift. This redshift not only shifts the color of light, but also acts as a record of time. The farther we look, the further back in time we see. Because of this, our telescopes act like time machines. We observe galaxies not as they are now, but as they were when the light we see first left them, sometimes billions of years ago. The Hubble Deep Field and James Webb Space Telescope images reveal the universe in stages, from near its infancy to the present. Yet space-time is not just a passive background. It has properties and dynamics. It can ripple, as seen in gravitational waves. These waves, distortions in space-time itself, travel at the speed of light, carrying information about cataclysmic events like black hole mergers. It's also possible that space-time itself had a beginning. According to current models, time emerged from the Big Bang, a singularity where classical physics breaks down. Before this moment, conventional time may not have existed in any meaningful sense. Some theories propose that time is emergent, not fundamental, but arising from deeper quantum phenomena. In these frameworks, what we perceive as flowing time could be a byproduct of statistical processes, entropy, or entanglement patterns. In quantum gravity, a theory still in development, space-time might be composed of discrete units or loops, like pixels in an image. This would imply that space and time are quantized, a radical shift from the smooth continuum described in general relativity. Experiments in this domain are challenging. The Planck scale, where quantum gravity effects become relevant, is many orders of magnitude smaller than what we can currently probe. But indirect observations, such as black hole evaporation or the early universe inflationary era, may offer clues. The arrow of time, why time appears to flow in one direction, remains an unsolved question. Thermodynamics suggests that time's direction is linked to entropy, the tendency of systems to evolve toward disorder. The low entropy beginning of the universe sets this direction. But on the microscopic level, the laws of physics are mostly time-symmetric. This tension between symmetry and experience lies at the heart of many philosophical and scientific debates. In cosmology, the arrow of time could be tied to the expansion of the universe. Some speculative models suggest that in a contracting phase, if such a thing ever occurred, time might reverse, or at least appear to do so. Others propose a multiverse, with different arrows of time in different regions. Despite its mystery, time is one of the most carefully measured quantities in science. Atomic clocks can now measure differences of less than a billionth of a second over millions of years. These tools help refine theories, test relativity, and even redefine the second. As we explore deeper into the cosmos and deeper into fundamental physics, our understanding of time will continue to evolve. Whether as a dimension, an emergent property, or a manifestation of entropy, time is central to the structure and evolution of everything. The universe is vast, but what we can see of it is limited by the speed of light and the age of the cosmos. This boundary defines the observable universe, a sphere centered on the observer, in this case, Earth, from which light has had time to reach us since the Big Bang. At present, the observable universe has a radius of about 46.5 billion light-years. This may seem counterintuitive, given the universe is 13.8 billion years old. But due to the ongoing expansion of space, light from very distant regions has been stretched across a much greater distance by the time it arrives. This expansion also means that some galaxies are receding from us faster than the speed of light. This doesn't violate relativity because it is space itself that is expanding, not objects moving through space. These regions lie beyond our cosmic event horizon, the limit beyond which events can never affect us, no matter how long we wait. In practical terms, this means there are parts of the universe we will never observe, even with perfect instruments and infinite patience. Light from those places will never reach us, because the space between is stretching faster than light can traverse it. The concept of horizons is central to modern cosmology. There are different types. The particle horizon marks the maximum distance from which particles could have traveled to the observer in the age of the universe, defining the observable universe. The event horizon delineates the limit beyond which events will never be seen by us, even in the infinite future. The Hubble radius is the distance at which the recession velocity of objects equals the speed of light based on the current Hubble constant. This radius is not a hard boundary, but a useful indicator of the universe's expansion rate. Within our observable sphere, astronomers have mapped hundreds of billions of galaxies, each containing hundreds of billions of stars. These galaxies form filaments, walls and clusters, separated by immense voids, in a structure often referred to as the cosmic web. Surveys such as the Sloan Digital Sky Survey, SDSS, the Dark Energy Survey, DES, and future projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, aim to map this structure with increasing precision. These maps help cosmologists understand how matter is distributed, how it has evolved, and how dark matter and dark energy influence the universe. One of the most astonishing aspects of the observable universe is the cosmic microwave background, CMB. This relic radiation is the oldest light we can see, emitted about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely. It forms a nearly uniform backdrop with tiny fluctuations that encode information about the early universe. Despite its breadth, the observable universe is only a small fraction of the total universe. Some inflationary models suggest that space extends infinitely, or at least vastly beyond what we can ever see. If inflation occurred as predicted, then regions beyond our horizon may have different properties, or even different physical constants. In this context, our observable universe is like a bubble in a much larger, possibly infinite cosmos. A concept that feeds into theories of the multiverse, where countless other universes, with different laws of physics, might exist beyond our cosmic horizon. But even within our limited view, the universe presents astonishing uniformity. The CMB is isotropic to 1 part in 100,000. The distribution of galaxies is statistically similar in all directions. This cosmological principle, that the universe is homogeneous and isotropic on large scales, underpins much of modern cosmology. Yet small variations, tiny differences in temperature in the CMB, or slight overdensities in matter, are what gave rise to everything we see: galaxies, stars, planets, and life. These primordial fluctuations, amplified by gravity over billions of years, seeded the entire structure of the cosmos. Understanding our observable horizon not only informs us about the size and age of the universe, but also sets limits on what we can know. It reminds us that some things lie forever beyond our reach, not due to a lack of technology, but due to the very nature of space-time itself. The concept of horizons also plays a role in black hole physics. The event horizon of a black hole shares mathematical similarities with cosmic horizons, leading to deep connections between cosmology, thermodynamics, and quantum theory, areas still being explored in cutting-edge physics. As we continue to study the universe, new instruments and theories will refine our understanding of what lies within our reach and what lies beyond. From this vantage point, Earth orbits an ordinary star in a typical galaxy, yet through the lens of physics, observation, and imagination, we can glimpse the contours of something unimaginably grand. As vast and complex as the universe is, humanity's ability to observe, question, and explore it has advanced more in the past century than in all of history combined. From ancient stargazers tracking celestial cycles to modern missions probing the edges of the solar system, our desire to understand the cosmos has driven relentless discovery. We now stand at the dawn of a new era in space exploration, one that extends beyond Earth orbit, beyond the Moon, and deeper into both our local celestial neighborhood and the universe itself. Space agencies like NASA, ESA, JAXA, and emerging players such as ISRO, CNSA, and private companies like SpaceX, Blue Origin, and Rocket Lab are reshaping access to space. The cost of launching payloads has dropped significantly. New spacecraft are becoming reusable. Satellites are being deployed in swarms for planetary monitoring, communication, and deep space navigation. The Artemis program plans to return humans to the Moon and establish a sustainable presence there by the end of this decade. The Moon, once a distant frontier, is now viewed as a staging ground for further exploration, a potential site for resource extraction, astronomy, and deep space training. Mars remains the most compelling near-term destination. Robotic explorers like Perseverance and Zhurong continue to analyze its surface, searching for signs of past microbial life and testing technologies for future human missions. Within the next 2 decades, crewed missions may land on Mars, conducting science on site and beginning the long process of understanding how to live on another world. Beyond Mars, missions to the outer solar system continue to expand our knowledge. The Europa Clipper, set to launch soon, will study Jupiter's icy moon Europa, investigating its subsurface ocean and potential habitability. Similarly, the Dragonfly mission will explore Saturn's moon Titan, a world with liquid methane lakes and a thick nitrogen atmosphere where prebiotic chemistry may be occurring today. At the same time, probes like Voyager 1 and 2, launched in the 1970s, continue their journeys through interstellar space, sending back data about the edge of the heliosphere. These silent ambassadors remind us that even small, aging spacecraft can touch the stars given enough time. Astronomy is also evolving. The James Webb Space Telescope, JWST, has begun transforming our view of the universe, seeing further and more clearly than ever before. It is joined by projects like the Nancy Grace Roman Space Telescope, designed for wide-field imaging and dark energy research, and ground-based observatories like the Extremely Large Telescope, ELT, and Square Kilometre Array, SKA. These tools will study exoplanets, probe the early universe, and refine our understanding of fundamental forces. Future observatories may detect biosignatures in alien atmospheres, confirm or refute inflationary models, and even image the surfaces of rocky worlds orbiting nearby stars. One of the most transformative developments in recent years has been the emergence of multi-messenger astronomy, the combined study of light, gravitational waves, neutrinos, and cosmic rays. This interdisciplinary approach allows for more complete understanding of events like neutron star mergers, supernovae, and black hole interactions. On the theoretical side, efforts continue to unite general relativity and quantum mechanics. String theory, loop quantum gravity, and holographic principles explore the fabric of space-time at its smallest scales, while quantum computing may one day simulate complex cosmological models with unprecedented accuracy. Meanwhile, philosophers and scientists alike grapple with the big questions. What came before the Big Bang? Is our universe one of many? What is consciousness, and how does it fit into the physical world? Are the laws of nature fundamental or emergent? Despite all we've learned, the universe remains full of mystery. Dark matter and dark energy dominate the cosmos, yet remain poorly understood. The fate of the universe, the nature of time, the origin of life, these remain open, beckoning us forward. Still, our progress is remarkable. We've mapped the cosmic microwave background, charted billions of galaxies, sent machines to distant worlds, and looked deep into space and time. And we've done so from a small, fragile world orbiting an ordinary star. From this vantage point, we see the cosmos not just as a backdrop, but as a source of endless curiosity, a stage for both majestic order and dynamic change, a place governed by laws we can understand, yet filled with phenomena that defy intuition. Whether it's the birth of stars, the dance of galaxies, the whisper of gravitational waves, or the structure of quantum fields, the universe invites us to listen, to learn, and to reach further. With every new discovery, the horizon expands, and with it, our sense of what is possible, not just for science, but for imagination, for meaning, and for wonder.